Ever wondered how AI models like GPT or BERT process language with such precision? The answer lies in a revolutionary architecture that's redefining the boundaries of machine learning. Today, we're diving deep into the technical heart of transformer models, exploring how self-attention mechanisms, positional encodings, and multi-layered networks enable these systems to understand context, generate text, and even translate languages with human-like fluency. This isn't just another AI overview. This is a breakdown of the mathematical and architectural innovations that power the models shaping our future. For decades, recurrent neural networks, RNNs, and their variants like LSTMs dominated NLP. But they had a critical flaw: sequential processing. Each word had to wait for the previous one, making parallelization impossible and limiting scalability. Then came the 2017 paper Attention is All You Need, introducing the transformer. This model discarded recurrence entirely, replacing it with self-attention mechanisms that allow the network to weigh the significance of every word in a sentence simultaneously. Think of it as a team of specialists, each analyzing different parts of a document and sharing insights in real time. No waiting, no bottlenecks. Let's get technical. At the core of the transformer is the self-attention mechanism. Here's how it works. For every word in a sequence, the model generates three vectors: queries, keys, and values. The query for a word asks, "What am I looking for?" The key answers, "What do I have?" And the value holds the actual information. The dot product between the query and key determines similarity, which is then scaled and passed through a softmax to produce attention weights. These weights are multiplied by the values, aggregating the most relevant information. This process happens in parallel across all words, enabling the model to capture long-range dependencies that RNNs struggled with. But wait, how does the model know the order of words? After all, it's now processing everything at once. Enter positional encodings. These are fixed vectors added to word embeddings, encoding the position of each token in the sequence. The original paper used sine and cosine functions of different frequencies, allowing the model to learn relative positions. For example, the encoding for position 0 might be sin 0 cos 0, while position 1 becomes sin 1 cos 1, and so on. This mathematical trick ensures the model isn't blind to order, even without recurrence. The transformer's architecture is built on stacked encoder and decoder layers. The encoder processes input data, transforming it into a series of contextualized representations. Each encoder layer contains a self-attention sublayer and a feed-forward neural network. The decoder, meanwhile, generates output step by step, using masked self-attention to prevent peaking at future tokens. This design is crucial for tasks like machine translation, where the model must generate a target sequence based on the source while maintaining alignment between tokens. Now let's talk about multi-head attention. Instead of a single self-attention mechanism, the transformer splits the query, key, and value vectors into multiple heads, each learning different aspects of the data. For instance, one head might focus on syntactic relationships, while another captures semantic meaning. These heads then combine their outputs, allowing the model to capture a richer, more nuanced understanding of the input. This parallel processing is what gives transformers their unparalleled ability to handle complex patterns. Of course, transformers aren't without challenges. Their quadratic complexity and sequence length, N2 for self-attention, makes them computationally expensive for long texts. Researchers have addressed this with innovations like sparse attention, linear attention, and models such as Longformer or BERT, which approximate attention to reduce costs. Additionally, the need for massive datasets and computational resources has spurred work on efficient fine-tuning methods like LoRA and parameter-efficient adapters. Transformers have become the bedrock of modern AI, but the journey isn't over. From causal language models like GPT to vision transformers and beyond, the principles we've explored today are evolving rapidly. Understanding these architectures isn't just for researchers, it's for anyone wanting to grasp how AI interprets the world. So next time you interact with a chatbot or translation tool, remember, it's the transformer working its mathematical magic, making sense of chaos one token at a time. Subscribe for more deep dives into AI research. Want to explore the math behind attention mechanisms? Check the description for links to papers and tutorials. Stay curious and keep learning.